My project title is Robust Tracking of Small Scale Mobile Primary User in Cognitive Ratio Network. In cognitive ratio has a great potential to enhance spectrum efficiency by allowing secondary user who are unlicensed user or devices to effectively utilize the spectrum opportunities temporarily unused by primary users. In cognitive ratios are key components of the efficient detection and reuse of spectrum opportunities that mitigating the spectrum scarcity problem that we may soon face due to the explosive growth of wireless or mobile users, services and application. Location information is very useful in cooperative sensing by enabling secondary base stations or fusion center to select an optimal set of sensor, especially when a very big primary signal like a WM signal is to be detected. Our secondary user must be able to accurately and reliably track the location of small scale mobile primary user or devices such as microphones in order to efficiently utilize the spatial spectrum opportunities while protecting the primary communication. However, accurate tracking of the location of mobile primary user is difficult due to the cognitive ratio unique constraint such as localization, which must be really slowly on the protected sensing results like measuring primary signal strengths. To cope with this challenge, we propose a new framework called Sequentially Monte Carlo combined with shadow fading estimation, abbreviated as SOLID, for accurate or fault-tolerant tracking of small-scale mobile primary user. Key idea underlining the SOLID is to exploit the temporal shadow fading correlation in sensing result, which is especially induced by the primary user mobility. By exploiting the temporal correlation in shadow fading, SOLID perform the following: improve localization accuracy by SMC combined with shadow fading, and also accurately identify the abnormal sensing report using attack detector. Next, SOLID reside at the base station and consist of the following three building blocks. First one is location estimator that tracks the location of a small scale mobile primary transmitter based on sensing results. And the second one is shadow fading estimator that detects and tracks the shadow fading gain at the cooperating sensor using the Kalman filter. Finally, the attack detector that detects and discards the abnormal sensing reports from the cooperative sensor and updates the normal profile in the base station. And the final one is our evaluation results. In high attack and fault tolerance of SOLID, our evaluation results shows that SOLID can detect and compromise sensing reports with high accuracy. Our extensive evaluation in realistic wireless fading environments shows that SOLID lowers the localization error by up to 88% in the absence of attacks and 89% in the presence of the challenging slow processing poisoning attack compared to the conventional SMC based tracking. Next, I am going to explain the data flow diagram for this project. First, create a cognitive ratio network. The primary is Primary user are defined as wireless devices that have to license to operate in a specific spectrum band. Primary user details such as name, location, coordinate, etc. that are stored in a base station. Primary user who have to rights to modify the system. In the secondary user, the person who utilizes the spectrum opportunity for communication is called secondary user. Secondary user are equipped with cognitive ratio to enable them to sense the presence of primary user and tune to the spectrum band which is not in use at any point of time for its own communication. They does not have any rights to modify the system. Secondary user use the solid framework to locate the primary user location. In solid framework contain the three baseline method. First one is SMC combined with shadow fading. Using solid employs sequentially Monte Carlo with shadow fading as a baseline scheme for tracking small scale mobile primary user. The key idea of SMC is to represent the recued posterior density function as a set of random samples with their associated weights and then compute the estimated location by taking their weighted average. In Kalman filter, we filter the unwanted nodes and noisy nodes. We are estimating the shadowing gain from using the Kalman filter. Solid accurately estimating the shadowing gain from the observed primary signal strength. Next, we are going to the attack detection for identifying the abnormal sensing result. A compromised or malfunctioning sensor node may report a falsified sensing value to the base station. To mitigate this problem, Solid verify the trustworthiness of the sensing reports and filter out the bad ones before performing localization using attack detection. Next, I am going to the implementation of the project. I am going to run the project. This is the title page of the project. Next, in this frame, the primary user details added node such as city, IP address, weight and X and Y coordinate. Next, we go to the base station. In the base station, we view the primary user details. Next, we go to the secondary user. Get the secondary user name and IP address. Secondary user use the solid framework to accurately detect the primary user location. Go to the solid framework. In solid framework, we find the weighted average and number of samples. Get the number of samples and get the weighted average from these weights. Solid framework contains three baseline methods. First one is SMC and Kalman filter and attack detection. First one is SMC. In SMC with shadow fading, get the number of nodes and the total weight. Enter the threshold value as 40 and weighted average is 4.5 and calculate the associate weights and coordinates and initialize the effective as 0, total weight as 36 and calculate the effective number of particles. Next, we find the location of the node. Enter the node, for example E. Check whether the nodes are there or not. Check if the node was found, then automatically enable the view button. View the location of the E node, city and IP address. Next, we go for the Kalman filter. In Kalman filter, we filter the unwanted nodes using the original set of the system and measurement of the system. Get the number of nodes and state noise filter. View the original set of the system and enter the number of measurement as 3, initial value of measurement as 0, measurement noise 0.01. Calculate the measurement of the system and enter the number of filter. 4. Enable the filter. Generate the input port according to the number of filter and filter the unwanted nodes or noisy nodes, and we go for the attack detection. In base station, we find the abnormal nodes. First we find the prediction error. Initial value of measurement as 0, measurement noise 0.01 and calculate the prediction error. From the prediction error, we find the prediction error distance. First calculate the Euclidean distance E1 and E2. From the equivalent distance, we find the prediction error distance. And we go for the attack detection. Initialize the blacklist count 0 and threshold value as 1. Enter the design parameter as 0. Count the prediction error count. Check the prediction error count greater than the threshold value or not. If it is greater than and the abnormal node was found, and enable the blacklist. Finally, the attack detection displays the abnormal nodes. Finally, we view the original state of the system, and next we go to the performance analysis of this project. In this analysis, the red line indicates the existing system and the blue line indicates the proposed system. The conclusion of the project is a solid framework which enables accurate and robust location tracking of small-scale mobile primary user in cognitive ratio network. Solid significantly improve the accurate tracking of primary user and filter out abnormal sensing results using attack detection.